Good morning, calculus class. This is Miss G, and it is Wednesday, April 22nd. I hope you had a great day yesterday. Today, we're working on section 5.4, area and fundamental theorem of calculus, but our specific topic today is properties of the definite integrals. So let's take a look at what they're all about. Let f and g be continuous on the closed interval ab. Our first property is the integral from a to b of k times f of x dx is equal to, or the same thing as, k times the integral of a to b of f of x dx, where k is a constant, a numerical value. So if you're multiplying a function by a number, you can take that number and put it right in front of the integral. Then you could find the antiderivative and do our definite integral, plug in the b, plug in the a, and subtract, and then multiply by k. All right. Today we're not going to be finding antiderivatives. We're going to be given the value of some integrals, and we're going to just use the rules. So let's see how that works. So for example, we can be given that the integral from 2 to 3 of f of x dx, some function, we don't know what it is, but we know that the integral from 2 to 3 of that function is equal to 4. Then the question will be, what is the integral from 2 to 3 of 5 times f of x dx? So that's this rule right here. You can take the 5 coefficient, pull it in front of the integral, and then you're left with here the integral from 2 to 3 of f of x dx, which they gave us as 4. So we just end up multiplying 5 times 4, and the answer is 20. So we don't have to find any antiderivatives and plug in any upper limits and lower limits. We're just going to use what they give us and apply our rules. All right, the next one says the integral from a to b of the sum of f and g, f of x plus g of x dx, is equal to the integral from a to b of f of x dx plus the integral from a to b of g of x dx. Now you already know this because we've been doing it in some of our problems, that you can split the sums and differences, the integral of sums and differences, into two separate integrals. So now what we'll do is we'll get that the given is that the integral from 2 to 3 of f of x dx is 4, and they'll also give us the integral from 2 to 3 of g of x dx is 10. And these will have the same limits, 2 to 3, 2 to 3, or we couldn't do them because they have to be a to b, a to b. So now they're going to ask, what is the integral from 2 to 3 of f of x plus g of x dx? Splitting it up, we get the integral from 2 to 3 of f of x dx plus the integral from 2 to 3 of g of x dx. And then we know what the integral from 2 to 3 of f of x dx, that was giving us 4. And from 2 to 3 of g of x dx, it's giving us 10. So it's just 4 plus 10, which is 14. All right, we've got a couple more to go. Let's see what we've got. All right, this is number 2 continued. It just shows that if you subtract two functions, the integral of the difference of two functions, as long as the limits of integration are the same, a to b, you can separate it into two separate integrals. So it's similar to the sum that we just did. So our example would be the integral from 2 to 3 of f of x minus g of x dx is equal to the integral from 2 to 3 of f of x dx minus the integral from 2 to 3 of g of x dx, which is 4 minus 10. Because we were given those values of 4 and 10. If we just look back, 2 to 3 of f of x dx was 4, 2 to 3 of g of x dx was 10. Now we're just subtracting them, so it's 4 minus 10, or negative 6. All right, number 3. Number 3 reminds us a little bit of geometry. So let's first recall from geometry. We had line segments in geometry, and if B was between A and C, then line segment AB plus line segment BC was equal to line segment AC. We sometimes call that segment addition. We sometimes called it the betweenness property, but AB plus BC equaled AC. And that was when B was between A and C. This segment plus this segment equals the whole segment. Now we're going to do it with calculus. Sorry, that was our geometry. So if we have an integral, let's look at the picture here. Here's our function f of x. And we have A and we have B this time. We don't have A to C, but we have A to B, and C is somewhere in between A and B. So C is between A and B. Then the integral from A to B, from here to here, all of this area, will be equal to the integral from A to C, plus the integral from C to B, here, of f of x dx. So it's kind of like our little geometry property here. What we have to keep in mind, though, is that whatever number or variable is between A and B, that has to be the same limit here. The upper limit here has to match the lower limit here, because we're going from A to C and C to B. Or we could be going from 1 to 2 and 1 to 2 and then 2 to 5. And that would give us from 1 to 5. So these have to match. All right, so let's see an application of that. So if we're given that, let's use this picture. The integral from 1 to 2 of f of x dx is 3. So let's say from 1 to 2, this region right in here is 3. And then the integral from 2 to 5 of this function would be this area in here, and that's 6. So if we wanted the integral from 1 to 5, it would be the integral from 1 to 2 of f of x dx plus the integral from 2 to 5 of f of x dx. And so from 1 to 2 was 3, from 2 to 5 was 6, and 3 plus 6 is 9. So that's our answer. From 1 to 5 is 9. Now I circle these limits. You don't really have to circle them. I just circle them so that you could see that this one has to match this one before you can do this betweenness property. All right, let's take a look at the next one. What do we have left? 2. These are a little easier. The integral from A to A. If the lower limit of integration is the same as the upper limit of integration of a function, then the integral is 0. So the integral from 3 to 3 of any function, f of x dx, is 0. Why? Because if we draw a little picture, there's f of x, and we're going to integrate from 3 to what? 3? That means we're not going anywhere. It's not like we're going from 3 to 5 and moving this over here and getting a shaded region. If we're going from 3 and we're staying at 3, then we haven't created any area. So our answer is 0, and the lower limit is equal to the upper limit. And the last one is the integral from A to B of f of x dx is equal to the negative, or the opposite, of the integral from B to A of f of x dx. So what did I do from here to here? I just switched the lower limit. It became the upper limit, and the upper limit became the lower limit. So I was going to do that all out for you and show you why, but let's just think about it. If you found an antiderivative, if this was some function like x squared, and you found the antiderivative, 1/3 x cubed, you would plug b in first, a in second, and then subtract. But if I switch it and I plug a in first into the antiderivative and b in second, the only thing that's going to happen is you're going to get the negative of the answer you got from the first integral here. All right, so in other words, if I integrate from 1 to 4 of f of x dx, that's going to be the opposite of the integral from 4 to 1 of f of x dx. Okay, all right, so those are the properties of integrals and of definite integrals. And so I have an assignment, section 5.4, page 348, number 7, A, B, C, and D, number 8, A, B, C, and D, and then on page 371, number 52, A, B, C, and D. So try that one, and then I'll post the answers to the even one in my next video. Okay? I hope you have a great day today, and take care.